Today we shall discuss an important topic which is called as selective leaching, or also called as dealloying, sometimes they call as partitioning. They all mean the same. Now, why does the problem of selective leaching occur in the first hand? Why does really it happen? It happens because it is concerned with the alloys. They are not concerned with the pure metal, they are concerned with alloys. Some examples if you want me to give, I can say that copper zinc, copper nickel, they are well known examples. Now, the question is, why do you really need an alloy? Why not we use a pure metal? Strength is a consideration, right? So, the strength is a consideration why you go for alloys. I want to give an example in relation to copper zinc and copper nickel. Now, if you take a, let us say, a material and then the properties, and the properties, what are the properties? Mechanical properties, maybe the yield strength, the ultimate tensile strength, and you look at the elongation, this is the percentage elongation. The units of that can be megapascal, and you can see you can appreciate how the alloying helps to improve the mechanical properties. Suppose you take a annealed copper, annealed pure copper. Copper is very pure. If you look at the mechanical properties, the yield strength of that is oddly 33 megapascal. The ultimate tensile strength is 209 megapascal. The percentage elongation is about 60. If you take a commercial pure, copper, take this, the strength increases considerably. Of course, the strength and the elongation are many times inversely related to each other. But if you take a brass, which is copper 35% zinc, which is annealed, right, you will see the strength increases quite significantly. In this case, even the elongation also is improving in this case. If you take, let us say, copper 10% tin, take this, you can see that the strength level is again increasing, and like this. If you look at the copper nickel, the alloy systems, say copper 10% nickel, I am talking about weight percent, the strength level is, the yield strength is 105 and the UTS is 275. The ductility varies depending upon cold worked or not, it can vary from 15 to 35, depending upon how they are done, it can vary quite widely. If you increase the nickel content further, say 30% nickel, see again there is an increase in the strength level, again it can vary in the range something like that. So, in essence we go for alloys because we want to improve the mechanical properties, especially strength of the metal. But if you look at this, we have seen earlier when you talk about the galvanic corrosion, when you have copper, when you have zinc as two different entities, a copper block and a zinc block, if you couple them galvanically in the environment, what is expected to happen? The zinc will corrode preferentially, it becomes an anode, and the copper will act as a cathode. So, the active metal dissolves and the noble metal gets protected. They are macroscopic. There is a clear entity of a copper block and a clear entity of zinc block. Between these two the current flows, right, copper acts as a cathode and zinc acts as anode, the current is flowing between them. But in an alloy, let us take a copper 35% zinc, which could be a homogeneous alloy, we will talk about it later. They mix it at atomic level, right, they are homogeneously dissolved, and more so in the copper nickel systems, right. The copper nickel system is known for having extended solid solubility. So, at atomic level they mix very nicely, but even then the electrochemical property of copper is different from the electrochemical property of zinc, or the electrochemical in the case of brass, and in the case of copper nickel alloy, the nickel is different from that of copper. So, you could able to see having a different electrochemical properties, and so you expect at atomic level exhibiting different corrosive behavior with respect to two different alloying elements. So, that is why we talk about selective leaching, or we call about the dealloying. Now, to just give an example how the system can become complicated, let us take this, the phase diagram. This is a famous copper zinc phase diagram. I think most of you might have studied in a physical metallurgy course, and you will see a lot of peritectic transformations, we call it. The copper zinc system, they exhibit different phases, right. When the zinc content is less, you have an alpha phase. As you increase the zinc content, what happens now? You can get a beta phase somewhere here. The composition lies between them, you get alpha plus beta phase. Of course, you have a gamma phase, you have epsilon phase, you eta phase, and so on and so forth. From the point of view of real engineering applications, the alpha phase and alpha plus beta phases are important. We call them as alpha brasses, we call them as alpha plus beta brasses, we call them as the beta brasses, amorphous metal. So, these are all very familiar with you. What I want you to understand is the amount of zinc varies depending upon the type of brass that you take. Now, why you take different brasses? Because they have different mechanical properties. The alpha plus beta brass will have a different mechanical properties. In fact, it could be much harder as compared to alpha brass. So, from the structural point of view, we need to use different type of alloys, which means they have different electrochemical corrosion properties. So, that is the crux of the matter. Now, these are some examples. You can also have various other alloy systems, and these processes are classified depending upon which element is selectively dissolving, selectively leaching. In a copper zinc system, you expect what, which one will dissolve first selectively? Zinc will dissolve, and you call them as de-zincification, a very familiar term. In the case of copper nickel, we call them as de-nickelification. You may have somewhat similar to copper aluminum, and aluminum can be with even other alloying elements you can have. We call them as de-alumification. Okay. Suppose you have silicon, we call D, and so on and so forth. These elements are selectively dissolved because they are relatively anodic compared to the next element. Sometimes selective dissolution, preferential dissolution is beneficial, right. For example, iron chromium, it is beneficial. Why? They form the passive films. Okay. So you need to contrast, and how this really are happening. Now, in order to use these alloys, let us say copper zinc, copper nickel, and whatever alloys that we talk about, we need to understand the concept of selective leaching or dealloying, we call it, in terms of mechanisms, in terms of the factors that affect the dealloying actually, and if you know both of them, then you can able to devise means to control dealloying actually. So, what we will do is, we will discuss now in terms of how this mechanism of dealloying occurs. There are about 4 different types of theory, important theories I would say. One, dissolution, redeposition mechanism. The second is volume diffusion. The third, we talk about surface diffusion. The fourth, we talk about percolation model. I will be very brief in discussing these mechanisms, okay, and they are fairly simple, they are not really that complex. Let us look at the first mechanism. We talked about dissolution and redeposition. Let us take the case of brass. A copper zinc in the system. In this alloy is exposed to the environment. We consider that both the alloying elements, they undergo dissolution or corrosion process like this. This is your step number 1. Okay. The step number 2, what is expected to happen here is, now look at this, you can have, look at this, in this solution your copper ions and zinc ions, the copper ions, the copper 2 plus equilibrium is nobler compared to zinc 2 plus equilibrium, right. So you have copper ions here, these copper ions would displace zinc ions, zinc in the lattice. So you have copper coming over as a copper here, over here. So you see now the copper ions in the solution will undergo a cementation process, we call it, right, we call it cementation process, wherein the zinc transfers the electrons onto copper ions and the copper ions get deposited, zinc dissolves as zinc 2 plus ions. So this is your step 2 process.
So this C2 plus is in the lattice of the alloy.
C2 plus is in the solution.
It's occurring in a solution.
Yes. See, I put it pictorially like this. Okay. Initially both they dissolve, right. Of course, it does not go from the bulk, it goes from the surface, okay, it goes to the surface. Then what happens now? What happens in this case? You have copper ions, they get exchanged, that leads to copper here, you have again copper here, zinc, copper, zinc, so on, right. So this is what is the displaced. So it is from solution, the solution consists of copper ions, the copper ions being noble, they replace zinc from the lattice of the alloy, okay, and the copper is getting redeposited. And you will form a porous structure. See, look at now, it forms a porous structure. It is not going to be a complete, a normal metallic structure. If this is the case, This is one mechanism that we talk about, right? Is one mechanism, and this theory has some limitations. For example, suppose you have copper gold, for example, or you have gold silver, for example, like this. The noble, so it need not get, and in this case, look at this. In this case, the gold may not dissolve, right? Only copper may dissolve, only silver may dissolve, because copper is quite noble, right? Suppose I give you a copper gold alloy system and put it in an environment, not necessarily that copper not necessarily the gold dissolves like you have copper dissolution in the brass system, because gold is noble in this case. So without dissolution of the noble metal, it is possible only the active metal can dissolve, right? So in this case what happens now? It is saying in this case it talks about the dissolution of only the active metal, the noble metal need not dissolve from the surface, okay. So it is really a selective dissolution and not a redeposition process. Do you understand the thing now? So this mechanism may not be valid in a system like that. Simply copper can dissolve and this can dissolve. It is done also, you know how people, how does the goldsmith separate the gold, right? The gold has got copper and gold, right? Ornaments, for example. How does he separate? He takes this one and melts with the silver and then forms an alloy and then pours it into the aqua regia solution. What happens now? Only silver comes out, okay. Copper of course comes out. Gold does not dissolve at all. So you can have a selective dissolution process wherein noble metal need not dissolve actually, okay. So this mechanism does not explain in those metals where those alloys where the noble metal will not dissolve at all. So there is no question of redeposition process. So you have the second mechanism which talks about the volume diffusion. Please understand the remaining three mechanisms we talked about, the volume diffusion, surface diffusion, the percolation model, may not invoke the dissolution of the noble element of the alloy. It could say that only the active element dissolves, the noble element does not dissolve in the system, okay. Now if that is the case, suppose I have a bulk alloy, let us say it consists of say copper and gold, something like that. In the surface, see you have a surface here. In the surface it is possible that only copper comes out and gold get enriched, right. So it is a selective dissolution. Of the relatively active metal, active element, and noble metal does not dissolve. So only copper comes out, gold remains on the surface. And there is a problem here. Can you tell me what is the problem? The problem is that the diffusion of the elements at ambient temperature is so low, right. If this process has to continue unless the copper comes to the surface, it is not possible for the dealloying to continue, am I right? For the dealloying to continue, the copper from the lattice has to diffuse and then come to the surface, and then only there can be dealloying. If it does not happen, a few atomic layers of the alloy will dissolve where the relatively active metal post solution, and then thereafter there will be no dealloying taking place, because the diffusivity is low at ambient temperatures. You might have heard of high temperature oxidation, right? There you talk about diffusion of aluminum, diffusion of chromium to surface, diffusion of silicon to surface, get oxidized, forms a nice protective film and all possible. But at ambient temperature, the diffusion of these elements are so low, you do not expect them to continue with the dissolution process. But however, what people have done, they have noticed that when there is a dealloying taking place, people have observed change in the phases. For example, if I take copper zinc system, I take zinc rich alloy, I take zinc rich alloy, okay, and when it dissolve, what happens? Just look at the phase diagram here, right. If I take an epsilon alloy here, then the surface will be alpha, then alpha plus beta, beta plus gamma, and gamma plus gamma. So it will go this way, right, because if you remove zinc from the surface, you will get more rich copper rich phase, right. So copper will, I mean the brass will have copper rich on the surface because zinc is removed. So as you move from the surface to the bulk, the phases will be alpha, alpha plus beta, beta, beta plus gamma, and gamma, and so on and so forth, isn't it? That is how it happens. So that is how people have detected in some cases to show that there is a selective dissolution of these elements. But however, the thickness of these layers are so small. So this theory is little bit a problem, but of course they have proposed what is called as die vacancy theory. They say that if you have two vacancies together, it is easy to migrate. So that is a theory that has been proposed, but it is not been well proven across various alloy systems. Okay. So the volume diffusion is considered to be more difficult, and it is not be very favorable for dealloying of various metals. There is something called as surface diffusion mechanism. This is very interesting. Now I have a surface, okay, and I get dealloyed. It is a dealloyed surface, okay, a dealloyed surface. When it dealloyed, then what will happen to the surface? Surface will be rough and porous, there will be atoms loosely held, right. Now these atoms migrate through diffusion process. Because when the atoms are alone, the energy of the atom, because surface becomes quite large, right. So when the energy of the surface is more, then what happens? They try to agglomerate, actually. So what happens? They migrate, diffusion process, and then form islands. of noble metal clusters, noble metal. You will see porous structures, porous, you see pits. So, the initial process is the active element dissolves, the noble element remains on the surface, but subsequently what happens? The noble elements, the atoms, they diffuse on the surface and they form clusters. In the process what happens? You are going to generate a free surface again, am I right? You can create a free surface because the atoms are moved and formed as clusters, so it creates a free surface that again leads to dealloying. So this is people have been modeling this and then trying to show that the dissolution is by clustering process. People have shown nanostructures, people have shown the porous structures, okay, and that's how and the dealloying continues. It's not just the surface process; it can go subsurface process. So surface diffusion process is a result of dealloying of the active element, the clustering of the atoms because of the surface energy, leading to creation of the fresh surfaces, and subsequently again there is a dealloying, and the process continues, and dealloying happens eventually to a larger thickness in the alloy, right. There is a small variation in this concept. This is called as percolation. You know what is called percolation, right? This model probably many of you might have studied, and various contexts of that. You take a solid containing A and B, any entities that you have, you mix them thoroughly, right? You mix them thoroughly. Suppose assume that A is the major element and B is a minor element, right? You mix them thoroughly, the B's can come in contact with each other when you exceed the concentration of B beyond a level, right? Do you get it? So when I have A and B, I mix it. If the content of B is very low, then all B are isolated, okay, or all the B are surrounded by A nicely. But if you keep on increasing B at one level, B and B will come in contact with each other, okay. So that means that makes a continuous path for the B to dissolve, am I right? When the B and B are coming in contact with each other, then it starts dissolving actually. So the percolation model tells that beyond certain concentration, the dealloying occurs. This is a very interesting theory. For example, take copper and zinc, less than 18% of zinc, no dealloying. If you increase the zinc content beyond that, the dealloying occurs. So the percolation theory talks about the active elements coming in contact with each other so that the dissolution path is quite continuous, right? It goes like that. But please notice that the percolation model and the diffusion model can work together, right? I can have some threshold level of active element that leads to dissolution, but even then there can be diffusion of the noble element in the surface so that they can form clusters. So, the percolation model does not totally exclude the surface diffusion model actually, right. So, it is quite possible. So, the percolation model explains why you need critical concentration of alloying element in order to get the dealloying. Without that it will not happen, right. So, that is an important thing when we talk about the dealloying of materials actually, okay. So, we will talk about factors affecting dealloying shortly, okay, but these concepts are important in order to understand the factors that control the dealloying of the metals and alloys, okay. Is it clear now actually? So, we so far saw 4 theories, one involving that both the noble element and the active element they dissolve in the first instance, and subsequently the noble element what happens, it deposits back onto the surface and it displaces and then the active element goes to solution, right. This is called displacement process. Yeah.
So in each of these cases there are 2 processes, opposite processes are occurring. First is the electrochemical, the difference in the potential between the elements, and second should be the thermodynamic kinetic property of diffusion. So in this percolation thing, still there is a potential difference between copper and zinc even after such a low dissolution.
Very true, yes.
So why is not that dealloying occurring? How is this theory accounting for that?
You are saying that why do you need a percolation model, right? This is what you are saying.
Yeah, because zinc here is active. It had to dissolve, not deposit like on the surface. Copper used to move around and then form pits.
Yeah, yeah. See now look at the model. For example, the dealloying model. I mean, in the redeposition model that we talk about, it is simply that at one go both the elements dissolve and they get redeposited into the system, right. In which case, irrespective of the amount of alloying element added, right, what I mean talk about concentration of element, right, the dealloying should continue to happen, right. It does not happen if you have copper zinc but is 18%, or famous red brass. Red brass you do not get dealloying, we will see later. Yellow brasses occur, okay. The yellow brasses and red brasses are all alpha brasses, but then the amount of zinc in red brass is only 15%. So 15% zinc does not lead to dealloying. Any amount of time you expose to the environment, nothing happens, okay. So how can you explain that? The only way that you can explain is that you need a critical concentration in order that the dealloying occurs. Now the critical concentration, how much is required, that also will depend upon what? It may depend upon temperatures, it may depend upon the environment, it may depend upon the 2 alloying elements. For example, if the alloying elements have wider potential difference, right, then the critical concentration may come down also actually, okay. The factors that you see a little later. So yes, they are all going to decide what is the critical concentration or threshold concentration above which the dealloying occurs, okay. But these factors are to be taken into account, which that is what we are going to see in the subsequent discussions. So the percolation model explains the need to have critical concentration of the active element in order to have dealloying process. That's what the discussion all about actually, okay. And the surface diffusion model is also proven because when you take out and see, there are islands, there are islands and there are, we are not going into details. If you look at the R.C. Newman's work and all, they are shown very clearly there are nano grains, okay. How you get a nano grains? They get nano grains because these atoms are get clustered and form the nano grains actually, okay. So the clustering they do happen, okay, and then since the nano grains are porous, and then there is a continuous dissolution of the metal really taking place at all. So so what is after all mechanism? The mechanism is what we propose in order to explain the observations that are taking place, right. That is what it is all about actually, and then these mechanisms should also explain the fundamental processes that are taking place. For example, when you say volume diffusion, the issue there is that how much, what should be the thickness over which this can happen. So this cannot happen, so they also used a theory called as divergence theory, but then still it is very limited. You cannot have extended dealloying of metals, it cannot take place at all actually. So that is why the volume diffusion was put forward by Howard Pickering in his own papers. So you see some papers appeared in corrosion science long ago, very nicely demonstrated that there are, if you see the surface, as I told you, the volume diffusion is what, when you dealloy it, the surface will have the least amount of active element. As you move inside, the active element concentration increases, right. That's why it is called volume diffusion of taking place, right. And so that he has proved, he has shown it by using electron diffraction pattern that these phases are changing from surface to this, but the thickness over which they are happening are very limited and taking place at all. So each of these theories is not that as though that there is no evidence, but there are limited amount of evidences, and each theory have their own limitations to explain the completely observed phenomena in the dealloying of the metals actually. Okay, I hope I have made the point clear to you in terms of these models in explaining dealloying of metals. Any other questions you have? Okay. So let us move on to the next one actually. Okay. What are the factors controlling now? This is called as partitioning, right. The partitioning will depend upon element A, which is noble, I call it, potential of the noble element, and the potential of the relatively less noble element we call as active element. Okay, I do not call anode and cathode active element, right. If the delta E is equal to En minus Ea is large, then dealloying increases. What does it mean? You take copper zinc and you take copper zinc and copper nickel. If I make a tube for a heat exchanger that carries seawater, one case it is copper zinc, other case it is copper nickel, both cases seawater is being used, which of the two tubes will fail earlier? Copper zinc will fail earlier, okay, that is what I meant here. So because the potential difference between these two are quite large as compared to this. And secondly is the composition. Higher the content of the active element, more is the dealloying. Right. Say an example, copper, let us say 18% zinc, copper let us say 30% zinc, and copper 40% zinc. This is these both are called alpha brasses, right, and this is called the beta brass, this is called the Moon's metal, right. The Moon's metal, famous Moon's metal is copper 40% zinc, right. So, the dealloying will increase from this to this and to this, am I right? Because the delta E is going to be the same, in all cases, but the content of the active element increases from this to this to this actually. Similarly, you can also have copper 10% zinc, nickel, and copper 30% nickel. The question then you will ask is, why would people use alpha beta brasses? In seawater people use alpha beta brasses. Why they use? Because the alpha beta brasses, they have better erosion corrosion resistance. They have better mechanical properties. So, the damage mechanism need not be always dealloying. It can be simultaneous process. When there is a flow line, there is velocity, you can have dealloying, you can also have erosion corrosion. If the erosion corrosion is more dominating, then what happens? Then you will see that copper 18% zinc will be failing faster than copper 30% zinc, because copper 30% zinc has got better mechanical properties. So you need to look at overall perspective in terms of the metal selection, alloy selection for given applications. Okay. But what we are seeing here is understanding the science of dealloying. So that I think you should try to understand. Now, in addition to this, it also depends upon the environment. More oxidizing environment, more oxidizing, more corrosive, more dealloying. An example is chlorination. People do chlorination in cooling water systems, and if you do chlorinate, chlorine is an oxidizer, and so the more dealloying occurs. Let me look at a slightly more related to alloy chemistry towards the dealloying. Okay. Okay. Let us take that I have element A and B. B is active, okay. So, the B concentration increases as you go from this curve 1, 2 and 3, the concentration of the active element increases. Now, they show some kind of passivity. And you have a potential here, and this is the potential we call it, okay, we call the potentials, and this is called as EC. Beyond this, selective leaching occurs. So, there is a driving force for corrosion to occur, right. So, for these alloys, in order to find out whether they undergo dealloying, how effective they are, you can carry out a polarization curve, okay, and get this and find out what is the EC value. EC here represents the potential above which the dealloying really occurs. And the increase in passive current density here, so called passive current density, means that there is more dealloying is taking place. Now, if the corrosion potential exists above EC, if E car is going to be greater than or equal to EC, then what happens? dealloying occurs, right or not? Because only above EC you have dealloying, you get these polarization curves. So how do you get E car at that particular value? What is the basis? When will the E car will go here? Yeah. In actual situations, when do you expect that will happen? What is the criteria for that? Yeah, that's right. You call it transpassive. I don't want call this a transpassive here. We call here these potential above which there is a dealloying taking place. When will the E car will go above this? Or what? So it depends upon the reducing reaction, right? You have one more reaction. This is your anodic reaction. You have a cathodic reaction. If the cathodic reaction, if the kinetics support that, suppose I have this is for cathodic reaction, it cannot happen. But if the cathodic reaction occurs somewhere here, what happens? The E car is going to lie above the EC, so you are going to have dealloying here, no dealloying here. So what I mean is the environment also is important. The environment is less oxidizing, then the dealloying will not take place at all. Okay, and this concept we have seen it shown many number of times. How the E car really occurs. The E car is a mixed potential, right? Mixed potential means it is both on the anodic as well as the cathodic kinetics. Okay, so it depends on the alloy, it depends upon the environment as well. That is the point that you need to be understanding at all. Now the EC, of course, it depends upon what? Depends upon the alloy here, right? If the EC will keep reducing if you are going to alloy more and more active element in the system. Yeah, it is not pitting here. You don't see a pit here in this case. That's why in copper, copper zinc system and copper nickel system, you don't get a pit at all actually. Okay, if you observe the surface here, you will see the surface is enriched more with what? With copper, because zinc is just getting out of it. Similarly, copper nickel also, nickel comes out of solution. In fact, if you take a copper nickel system, if you carry out a polarization here and see the solution color will turn into green. Why? That more nickel is getting dissolved. So you see a nice green coloration at this particular potentials. You may see nickel also here, but then the amount of coloration you see very small here. So that's where you can able to show that nickel is preferentially dissolving over this particular potentials. Okay, hope this point is clear to you. Now we have seen these things, that what does it really means in practical applications? Okay, application, where are these problems? I am not sure to what extent you can able to see this picture here. Okay, let me try to see. You see this black coloration here. They are greenish black color actually. I don't know how far it is able to see. And this is a copper nickel alloy in seawater application in one of the refineries located in Mumbai. It's about a couple of years. Through this the water, seawater, was passed through. This is heat exchanger. Now you see the coloration here. I hope you are able to see this coloration here. So this is the coloration they will see. Look at this color. You can able to see this color here is bright here, right? That is, and this the black thing that you see here is due to the de-nickelification. The nickel came out of surface and formed this actually here. Okay, this is something which is which normally you see. This is another example. This is another example of how the dealloying can really affect. This is essentially it's a de-zinkification process. The left side, what you see here, this layer is a dealloyed layer. Okay, you can see this. It's rich in copper. But look at this. This is a layer type. Here is something like a pit type. You see here. So you can have two different types of dealloying taking place. It depends upon the alloy. It depends upon the environment. You can have you can have a plug type, this is called a plug type, this is called a layer type. So, if we have like this, please notice now if I remove zinc from brass, what will happen? What will happen to strength? Reduce, because that is what is giving point. So, the strength will reduce actually, okay. And in this case it not only reduces strength, it also brings stress concentration at this kind of pits here, okay. So, this is the other kind of problem. So, these are the real problem happen, but fortunately they are not, the dealloying is not as fast as your pitting corrosion and all, but yes, it does affect over years, okay. And in this case of course this is an accelerated one, acidified copper solution, so 7 days only, but in practice it may take a couple of years to get the dealloyed layers actually on the surface.
Is sensitization same as leaching?
No, sensitization is not a leaching there, right. In sensitization what happens now, in sensitization you are talking about stainless steels, right. In stainless steels you are taking the chromium out of the grain boundary area, right. So, you are going to have simply iron, so iron simply dissolves there actually, is it not, okay. And if you have, in fact this goes other way around, if you are going to have a stainless steel and iron and chromium dissolves preferentially and it forms a nice passive layer, it stops actually. In fact, a sort of selective corrosion is happening in stainless steels, okay. But only thing that happens now, the chromium forms a film, so it does not allow the subsequently the dissolution of the alloy. So, dealloying in some cases can be beneficial, okay, it can help, but in these cases where it is not passivating, it is not good, because it is going to be reducing the strength of the alloy significantly and cause the problems, okay. Yeah. So, applications, now you see that you have alpha brasses are prone to this, to dealloying, which is of course beyond 18%. Alpha brasses, alpha beta brasses and alpha beta brasses, all of them are prone to dealloying actually. What people have done actually in order to avoid this, the dezintegration process, alpha brasses, you might be knowing what is called as Admiralty brass, right. I think people from the Navy knowing it is Admiral who first formulated this particular alloy actually. So, that is why it is called as Admiralty brass. The Admiralty brass, it consists of tin, okay, it has got a tin, I think it is about I think it is about 1%, I think it is about 1 weight%, yeah. So, about 1 weight% of tin is added to this, okay, to alpha brasses. To support this, they also add small quantities weight% of what, of arsenic, antimony and phosphorus are added to this, and they are effective in curbing the dealloying of alpha brasses. The mechanism is not completely known, this is not known actually, okay. There are some speculations, but not completely known. But alpha beta brasses, such additions do not help. So, they continue to undergo dealloying, same as the beta also, right. And for most seawater application where you want to really have a safe thing, people go for copper nickel systems, people go for copper nickel alloys, seawater people use that predominantly. I will just cover another topic which is relatively small and related to dealloying, and this is called as graphitic corrosion. Yeah, I mean, see, in the solid state diffusion of all these elements, at ambient temperature is very, very less, very small, right? It's extremely slow actually taking place, and I don't think zinc also the diffusivity is any significantly higher compared to that. Okay, so the diffusivity of zinc in copper is still is very low. If the diffusion is going to control the dealloying, right, then the rate of dealloying will be very, very low. Okay. Now, then how do you explain the rate of dealloying which is higher? Okay. So, that is the question that comes now. Okay. Now, the bulk diffusion, the volume diffusion model, that if you want to account for the rate of dealloying, it cannot be accounted based on the diffusion, diffusivity of zinc at ambient temperatures. A bit of the use of the die vacancy, that means to say that there are two zinc atoms which are dissolving and creating two vacancies, and two vacancies are move little at a faster rate, and so that assists the diffusion, migration of zinc from the from bulk to this. That is a speculation, that is speculation taking place. Otherwise, simply based on the diffusivity of zinc in the lattice at ambient temperature, you cannot account for the rate of dealloying occurring in process at all, these things. So, that is where the volume diffusion theory lacks in explaining the experimental observations. So, we are going to go into surface diffusion, because in surface diffusion what happens is you are simply clustering, right. The reaction, the dealloying is always happening in the surface only, it is not happening at the bulk. When you have, let us say that zinc is coming out and you have copper, you may have a copper atom which are free atom there actually, they just move and they form islands of copper, right, which means they are clustering, that means the free surface is done. Now, these islands also start growing like in two dimensional things now. So, that means you always have created a free surface, and through the free surface the dealloying is taking place. So, there is no bulk diffusion that is accounted for in the surface diffusion process. So, that is why you are able to talk about it, and people have done that. Actually, again Newman model is looked at Monte Carlo simulation, and then trying to see how these are happening and all this they have done it. So, that explains one part of it. The other part it does not explain is that why you need a threshold level of the active element in the alloy in order to cause the dealloying, that does not really tell. Okay, that is where the percolation model comes into pictures, because you see here what it means is that there can be surface diffusion, but surface diffusion is not enough to account for the dissolution rate of it, right. So, in addition to this surface diffusion, the percolation model which connects the active element in the matrix, it dissolves and then it goes to connect like this only. Okay. So, these are all, in fact, we would talk about even composites and all, people talk about composites, various properties, the electrical properties of the composites, for example. Okay, they are isolated, then the electrical property does not happen. Suppose you have element A and element B, the element A is insulator, and you add element B into the system actually, and beyond certain level of B, which is conducting element, you see a nice conductivity increases, because the B is connecting each other to the pathways actually. So, this is essentially that you are connecting them, and then through the pathway they come as a channel and dissolve out of it. So, it is another way of looking at the selective dissolution of the atoms actually. Okay. So, they are not isolated. So, percolation model talks about critical concentration required for that. Okay. But all are again related to potential difference related to the environment, because the driving force for the corrosion again depends upon the other factors. What? The potential variation, the environment that you are going to be here, the ECAR value that shifts, they are all going to be a part of, which talks about the rate of dissolution of dealloying. Okay. So, these two things should be seen separately, the factors and the mechanism are to be seen, should be properly understood, I would say, I think. Okay. That is the thing. Is that answered now your questions? Okay. Any other questions if people have? Okay. Now, let us go into the graphitic corrosion. I just want to finish up this here. People have been using cast iron pipelines. Those who are not familiar with cast iron, we just spend a minute, okay, to get an idea about what it is. What is the difference between a steel and a cast iron?
Castable grade.
Okay. Oh, so, what is the composition of carbon?
From 2 to 4% of carbon or greater than 2 weight percentage.
So, more than 2%, 2 point something like 4 or whatever kind of 8%, if the carbon content is going to be there, okay, if the carbon is more than that, you get into cast irons. Can you give a better definition of that? It's right?
Laws of iron and carbon that can be casted.
I can cast anything I want. I can
The
cast.
presence of eutectic phase in this.
You are right, yeah. So, in the solidification process, it does not go through from the liquid, it does not go through this, it does not go through a gamma transition, right, isn't it? If you look at the iron carbon diagram, in all the cases, the liquid directly can give rise to what? Give rise to alpha plus Fe3C can give, right, can give us, okay. You can give alpha and then you can give rise to alpha plus Fe3C. So, it does not go through a gamma in the phase diagram, first of all, first thing. The second thing is it can form a cementite along with alpha, or it can also form alpha plus graphite. Am I right? Now, of course, there are different types of cast irons, which is very famous, grey cast iron, white cast iron, nodular cast iron, or one more, malleable cast irons. What is the difference between a malleable cast iron and a nodular cast iron? Anything more? Iron is converted to malleable cast iron by heat treatment process, right? Whereas the nodular cast iron goes directly from the liquid, you get the graphite actually there, okay. And what is the grey cast iron? Here also you get a directly you get a graphite, but the graphite is in what form? It is in the flake form actually, okay. Now, you please read those people who have want to know more about, for example, why should it form Fe3C, how is possible for you to move without forming Fe3C, how you can have graphite, what are the additions that are added, all this you can read some books, and there are nice books available, simple books, if people read it. Now, it is important for you to understand the microstructure of cast iron in order to understand what is called a graphitic corrosion. This is a grey cast iron, right. What you see, these flakes are all what? These flakes are all graphite, right. The matrix is a ferrite, alpha matrix. This is a grey cast iron. But what you need to know is these flakes, they may look a little isolated. Are they isolated? They are interconnected, right. These are all something like so. If you have a thickness, suppose you have a thickness of the cast iron, a flake may start from this end, it may end in this end actually, right. So, these are all not isolated, they are interconnected in the grey cast iron. This is a very important thing, and for those who have not an idea about grey cast iron, you should know this. If you take a spheroidal cast iron, this is microstructure of this. Please notice these are graphites, graphite. These graphites are not only spheroids, spherical, and what difference does it make between the grey cast iron and this? They are not interconnected, they are well separated, right. They are well separated. That means each of this are surrounded by the matrix, okay. It has got then good mechanical properties as compared to grey cast irons. But anyway, we are not going to discuss that aspect, but these microstructures have relevance for corrosion. That I think we should be understanding at all. Please understand, you have a graphite in the system, you have alpha in the system, which alpha means is iron, a little bit of carbon dissolved there, okay, and so that is what you normally see in the system. So, what is the consequence of that? This alpha ion, so graphite here. I expose to the environment, right? There is an environment here, what happens? What do you think will happen? I have taken this alloy and exposed to the environment, maybe like sodium chloride solution or water, moisture, something like that. So, what do you think will happen? The iron will dissolve preferentially. Why does it happen? Yeah? Yeah, so graphite is noble. So, if you look at the galvanic series, I hope you will be able to recollect the galvanic series we have shown before. Graphite is noble, iron is active. So, what is going to happen? You are going to have micro galvanic cells. It is not a typical dealloying like what you see in the in your brass or maybe in cupro-nickel alloy system. Here there is a distinct graphite phase and there is a distinct matrix of alpha ion, and so they have a different noble and active characteristics, and one which is noble will act as a cathode, the one which is active will be suffering corrosion, actually serious corrosion here. So, what will happen? You will see the corrosion occurring in the interface, the corrosion becomes severe, right. In the galvanic corrosion, where is the attack more? or the interface. Okay, the interface corrodes. Now it corrodes like that. If you visualize this, so what will happen here? In this case, the corrosion, suppose here is the environment here, the corrosion starts, it will proceed like that, proceed like this, proceed and start leaking here. Because of continuous thing, it leaks. On the other hand, if I take a nodular cast iron or a malleable cast iron, if you take a cross section like this, I may have some graphites here, and I have here, like this, right. Now the corrosion will start here, start here. Now what happens? They fall off. Now subsequently what happens to galvanic corrosion? It stops. The galvanic corrosion does not proceed further. The microgalvanic corrosion does not proceed further. So that what happens now? That means no graphitic corrosion. Now the graphitic corrosion that occurs in the grey cast iron obviously depends on the environment, right. See, so it's a pipeline, it is the soil chemistry becomes important, right. You have, for example, you have an acidic soil and you have a lot of chlorides, the attack becomes more, okay. Nowadays they are not much of a problem because nowadays people do not use grey cast iron that much because people have come to know there is a problem. Earlier days when there were pipelines, and the pipelines, in fact the problem started when they were paving the roads, okay, when they start digging the roads, the excavator, the shock waves that went and hit this pipeline caused simply the cracking, right. See what happens, imagine that I have a dissolution process here. What happens now? All the iron slowly dissolves, there is a residue of graphite just sitting on the surface, right. So it loses its mechanical integrity at all, and so even a small impact given onto the pipeline, it just fractures, okay. So these were the problems, just after Second World War, okay, there are a lot of problems. But nowadays of course people are very clever, they do not use grey cast iron, but it is important for us to understand the science behind this and why we do not use the grey cast iron for many of the pipelines, but cast irons are good. If you compare the cast iron versus the steel, generally the cast irons corrode at a lower rate. I am talking about uniform corrosion, because the cast irons may have some silicon, all the stuffs which they are generally more resistant to uniform corrosion. But if you have grey cast iron, the problem comes out of the localized attack that happens between the graphite and the iron matrix, leading to leaking of the pipelines. People in those days were storing even sulfuric acid, using the cast iron tanks, and sulfuric acid will leak from inside to outside. Whole structure looks very intact, but it ooze out because the corrosion occurs between the graphite flake and the matrix, and so start oozing out from the surfaces. So only way to avoid here is that not to use grey cast iron, people use what is called as malleable cast iron or the nodular cast irons, okay. So that should bring us to the end of the discussion related to the dealloying and the selective leaching, and I wanted to go through this and